Hello, I am Byung-Soo Kim. I'm gonna start my presentation about advanced topics in physics 2. My research is to focus on to the saturable observers, which means of the optical components make a very short wavelength pulse generation components. So the principle of the saturable observer is the uh, low intensities have a high losses and high intensity have a low loss. It can be make a very short pulse like this. So we use the non-linear optical properties of the materials. We can make a very short pulse lasers by using a saturable observer. Here is some type of the saturable observers. This is the optical fibers. So this A and B is based on the end phase type of the saturable observer. C is the side forest fibers, and D and E have a tapered fibers type of the saturable observer. So the basic principle is the materials and light interaction can be make a very short pulse lasers. So the diffusion method is well known about other researchers, such as the physical vapor diffusions and chemical vapor deposition like this, and it can be make a very large and very efficiently to make a very thin film. And materials of the saturable observers is development firstly the sesame and have using nanomaterials, CNT, and the next few decades is the 2D materials such as the graphene oxide and topological insulators and TMDS and black phosphorus like this. So my research goal is that the first I development of new optical diffusion method and make a saturable observer by using this method and tunable wavelengths and I will talk about later about the liquid saturable observers. So this is the schematic diagram in my research. First thing is how to make a thin film deposition like this. And this is the laser cavities, conventional laser cavities, and make a C-double laser generation. But we adding some optical components name is the saturable observer, we can make a short pulse lasers. So I use the graphene oxide solution and a very small size of the graphene oxide solution. I successfully to make a very thin film. So the immersed the optical fibers in the graphene oxide solution like this. And after that, we adding electrical arc by using the fusion splicers. And the fusion splicers arc is to make a thick film of the graphene oxide. And finally, we use the laser link cavities and using laser-driven self-explanations. And we can make a very short pulse lasers, which name is the Q-switching lasers. And we also tuning about the air gap between the optical fibers, and it have some filter structures. Name is the Fabry-Fabry filters, and this red one and a green one, and the violet one is the makeup filter structures, and it make a tunable wavelengths like this. So in summary, firstly we development of the optically optimal diffusion method and a very small amount of the solution in a few millisecond electrical arc, we can successfully to make a saturable observer and tunable wavelengths. So this is uh, the experimental setup in my research. We basically use the LED in the 980 nanometers and EDFA open of the 5 lasers. We adding the saturable observer like this. This is the air gap. This part is the graphene oxide thin film in the core. And this is the OSA optical spectrum analyzer, and oscilloscope and RF spectrum analyzers is the measurement system and measurement result data like this. So this is the end of the result data, which indicated conventional Q-switching lasers, and we can make a very tunable wavelengths and even dual wavelengths because of the dual filters make like this dual wavelengths. So we also do numerical simulations, which name is the Fabry-Ferro interferometers. We setting the SMF single mode fibers and graphene oxide thin film, and the between distance is the 8 micrometers. And we also do the experimentally try to make a filter structures, and this is the simulation data, and this is the some interference patterns like this, and this is the core and air and graphene oxide and the core part. So in this the core part and air part is make a Fabry-Ferro interferometer like this. So here is the graph of the result data, which means the black one is the Fabry-Ferro simulation, and the blue one is the experimentally we measurement is set up, and a red one is the laser output, real laser output. So in this peak is the well matching to the laser output data. So we can make a Fabry-Ferro filters cause the laser output like this. So here is the table. Table is we make based on the oven of the fibers. We make a longest wavelengths in the L band, and maximum peak power we got it, and also we have some high pulse energies and maximum output powers. We also get other compared to the different materials based on the C and L band, and we also tunable wavelengths in the C band to L band, and even dual wavelengths we also achieve that. And I'm gonna start to other materials, such as the previous one is the solid state sexual observer, but in this part is the liquid sexual observer. So the concept of the liquid sexual observer is the type is the two. One thing is the solvent type, which is the water or ethanol like this. We can use their high and large absorption of the solvent. We can make a sexual observer. And another thing is the solution. Solution combination of the materials and solvent. We can use the material absorption, such as the material is the graphene oxide, perovskite, MOS2, WS2 like this. And a solvent is the must have ultra low absorption, and it can be make a very short wavelength pulse generations using materials. So the advantage of the liquid sexual observer is the fast fabrication process and simplicity of the their fabrication, and also have high optical damage threshold because of the self-healing features of the liquid, and we can see the real-time pulse lasers measurements, and by tuning the air gap, we can make a different modulation depth control and a wide wavelength operation and a good summer diffusion and high performance output like this. But the disadvantage of the liquid sexual observer is the evaporation and the convection of the light. So we can carefully to deal with about this liquid sexual observer. And the structure of the sexual observer like this blue one is the SMF single mode fibers, and this cylindrical structure is the glass fiber, such as the mechanically connected optical fibers, and we filled in the solution or solvent, some materials, and we can connect it, and it will be make a very short pulse lasers. So here is the 2D perovskite liquid satural observer. So we use the high linearities of the perovskite and mixing the DMF with ultra absorption solvent, and we can tune the wavelengths about the conventional cavity. So we firstly reported about the saturable observer of the perovskite, and also have the tunable wavelengths about 7 nanometers, and we achieved the very large pulse width of the perovskite saturable observers. And we first reported about the Q-switching lasers about in the air band. So this is the importance and potential and application of the saturable observer and ultra-fast lasers. So as you can see, the very high energy pulse lasers, it can be make a very high damage about some material surface. So it can be reused about the industry or the military, such like that, and very in this case very long pulse lasers, such as the microsecond laser. But we go through the femtosecond laser, we can be make very precisely to control the pulse laser. So we can fabricate it very exactly fabrication of the industry region. So here is the summary of the application of the short pulse lasers, such as the medicals and basic science and industry processing and secretary, astrophysics and lithography and fusion energies and so on. So this application of the ultra fast laser is very widely used our life. So this is the summary and conclusion in my research goal is that I make a new deposition method name is the laser induced self exfoliation, and because of the Fabry-Ferro interference, we can make tunable wavelengths given laser cavities. And we also achieved a new area of the saturable observer materials, name is the liquid saturable observer, by using solution and solvent. And I also trying to using ultra-fast lasers and application of the optical fiber sensor and laser-induced breakdown spectroscopy is really, I try to make application of the ultra-fast lasers. So thank you for this is my presentation. And thank you.